Hello, grade 9. Today, inshallah, we are going to talk about lesson 11.3, which is exponential growth and exponential decay. We talked before about exponential function, and today we are going to study two branch for the exponential function, which is one of them is growth and the second one is decay. The diagram below highlights important concepts of the exponential growth and exponential decay. So if we look at this diagram, so if I want to make a summary about what we are going to study today, so we will divide the functions, the exponential functions, into two branches. The first branch is exponential growth, while second branch is exponential decay. The exponential growth, we will find that we have increased. Exponential decay, we have decreased. So we can say as a joke, dd, which is decay, it will be decrease. So we have a change with exponential growth, increase, and exponential decay is decrease. We have different formulas we are going to study it today. The first one belongs to the exponential growth. With the exponential growth, we have y equal a, open a parentheses, 1 plus r all to the power of t, where a should be more than 0. So let's know what is the what the meaning for each variable in this equation. Y equal final amount, a equal original amount, r the rate, and it's better to write it in a decimal form, and t is the time per year. So if we are talking about exponential growth, so we will note that we have a formula is plus 1 plus r. But if we are talking about exponential decay, you will find that the formula is 1 minus r. Also in this lesson, we are going to talk about compound interest and half-life. And both have formulas that involving an exponent, and both have many real life applications. So we will talk about compound interest and we will talk about half-life. And each one, it has a formula. So if we want to talk about the compound interest, it will be A equal P open parentheses 1 plus R over N all to the power of NT. And B, donate for original amount, T for time, R for rate, and N means times compounded. Half-life, A equal, the formula is A equal P times 0.5 all to the power of T. And we have to know which variable, sorry, the meaning for each variable, which is P, the original amount, and T is the half-life in this period. And after a while, I'm going to give an example for each one. But at the beginning, we have to know what is the difference between exponential growth and exponential decay. Let's move now to take an example about each one. As I said, exponential growth and decay, if the exponential growth and decay formulas, as we know that y equal a 1 plus r all to the power of t, and the second one is y equal a 1 minus r to the power of t. Let's take an example. The population of a city is increasing. So is increasing, so this one, it will back to growth at a rate of 4%. So 4%, it will represent the rate. If I want to change it into decimal form, so we are going to put it 4 over 100, it will be 0.04. In 2000, this is the starting amount, 2000. There were 236,000 people in the city. Write an exponential growth function to model this situation, then find the population in 2009. Then don't forget that started from 2000 and then finish at 2009. So what is the period which we are looking for? It will be equal 9. 2009 minus 2000. So step one, we have to identify the variables. We will look at the equation at the top. So we have to search about where is the original amount, which is A. It was 236,000. And where is R? It's 0.04. And where is T? T is 9 years. Then we will write at the beginning, because if you will back to the question, he said write an exponential growth function. So this is the first part from your answer. We will write first, substitute for the formula, y equal a 1 plus r all to the power of t. Then y equal 236,000, 1 plus 0.04 t. We will add, or we will simplify 1 plus 0.04, and this one it will be now 1.04, and this one represents the growth because it's greater than 1. Now we will substitute t, as I said, t for 9 years, from 2000 to 2009. Then it will be 335,902. So the population will be about 335,902. Let's take the second example. The population of a city is decreased, which means it will be decay at a rate of 6% each year. In 2000, there were 35,000 people in the city. Write an exponential decay function to model this situation, then find the population. By the same way, we have to identify the variables first. So which one was the starting amount? It was 35,000. And what is our, the rate was 6%, so it will be 0.06. After that, we will substitute, and don't forget, this one was decay, so the formula, it will be minus 1 minus r. Then we will substitute. When you compound 1 minus 0.06, you found it's 0.94, and it's less than 1. For this reason, it's decay. We will substitute, and then we found that the population will be about 16,657. So this is how we can use exponential growth and how we can use exponential decay to calculate from real life applications. Let's move to the next part from our lesson today, which is a special type of exponential growth involving finding compound interest. So for exponential growth, we have a special case, which is called compound interest. With compound interest, A equal P 1 plus R over N all to the power of NT, where is A is the total balance after T years. So we can use compound interest when you are going to deposit money in a bank for a long time, or when you are going to take a loan from the bank also for a long time. So we have something called compound interest. We studied in grade 8 simple interest, which it was interest equal principal times R times T, and this is called simple interest. But today with exponential growth, we are going to study compound interest. Then A is the total balance after T years, B is the original amount, R is the interest rate, N is the number of times that the interest is compounded in 1 year. T is the number of years. Let's take an example. Write a compound interest function to model 15,000 invested at a rate of 15,000. This is the time at the beginning. At a rate of 3%. Don't forget that we will change it into decimal. Compounded quarterly. So we are going to keep it for a quarter. So for this reason, N here is 4. Then find the balance after 8 years. So if I want to write the formula first, so it will be A equal 15,000 times 1 plus 0.03 over 4. And as I said again, why did you put 4? Because he said quarterly. All power 4 times t. T, he said after 8 years. So we are going to substitute the value of t by 8, and then we will multiply 4 times 8, it will be equal 32, and then we will simplify the answer, it will be 19,051.67. This is the balance, it will be after 8 years. As we said that we have a special case with exponential growth, we have another special case with exponential decay, which is involving the half-life of substances. The formula is A equal P 0.5 T, where A is the final amount, P is the original amount, T is the number of half-lives in a given time period. Let's take an example. SMAP 212 has a half life. So this one is a type for a virus like COVID-19, SMAP 212, so it's type of virus, has a half life of approximately 60 seconds. Then this virus have a half life every 60 seconds. Find the amount of ISMAF 2012 left from 25 gram sample after 300 seconds. Then he has half-life every 60 seconds. Then we have to find the T. It will be 300 divided by 60 equal 5. We will substitute P and T. P at the beginning, the starting was 25 times 0.5 because it was already in the original formula 0.5 and the T was 5. Then the amount after 300 seconds, it will be 0.78125 gram. This was our lesson today. So please don't forget to work with the lesson. You can answer your question. Don't hesitate to send me your questions. Best of luck, grade 9.